This is lesson 2 in chapter 4. We're going to be talking about chemical analysis and begin our conversation with a little bit of information about the discipline of chemistry as far as a job is concerned. There are basically 5 main branches of chemistry. There's organic chemistry, and you had a chapter on that, chapter 10. There's inorganic chemistry, which is all the other chemistry. Organic chemistry is all about carbon. Inorganic chemistry does have some carbon in it, but not carbons connected to hydrogen. Some carbons connected to oxygens like carbonates. Then you have analytical chemistry, which we'll be focusing on here. Then there's physical chemistry, and then biochemistry. So you're familiar with organic chemistry. Most of first year chemistry was inorganic chemistry. And you focused on metals and minerals and materials and basically those things that did not have carbon in it other than carbon dioxide and carbonate. Carbon compounds that are connected to hydrogen would be organic, and carbon compounds that have connected to oxygen would be mostly inorganic. Physical chemistry studies just the physical properties of matter. We need to understand their structure in order to understand those properties, because structure determines function. We focus a lot on the energy that is gained or lost, or we should say endothermic, exothermic, required or released. And then biochemistry is, if you're interested in the intersection between biology and chemistry, you go into biochemistry. Now, there are sub-branches to these 5 main branches. You'll have people that'll go into environmental chemistry. I have an interest in nuclear chemistry because you focus on the nucleus as opposed to the electrons that are involved in bonds and redox reactions and things like that. There's a subsection of organic chemistry called polymer chemistry, where you learn how to synthesize organic compounds or identify organic compounds. You make polymers and you study the properties and applications of those polymers. There is theoretical chemistry, where you do an awful lot of math and you also use some pretty fancy chemistry software in order to do computational types of chemistry, where you actually try to make some predictions and see if they might bear out in experiments by other branches, trying to explain some of the things that are difficult to explain from a modeling point of view. There's astrochemistry. So if you're studying outer space, especially if you're interested in the chemistry of what's going on in terms of the geology and chemical reactions that may or may not be on the surface of a planet, or a comet or an asteroid. Astrochemistry would probably also include some biochemistry, where you're interested in understanding whether or not some other location in our galaxy might be able to support life. Then you have geochemistry, just like you have the geochemistry involving the Earth, which is primarily what this is about. And you're talking about the different layers of the Earth, from the crust to the mantle, to the liquid outer core and the solid inner core, and the interactions between them. And then you've got, of course, medicinal chemistry. And you're working on designing drugs, synthesizing them, maybe identifying them out in the environment somewhere, and developing new drugs and new pharmaceuticals. So those are, it's a pretty wide and diverse field of chemistry, but it all begins with the course you're taking right now and the course you took last year. And once you have that solid foundation, you're going to find an area, if you pursue chemistry, that you're very interested in and you want to pursue. Having a solid chemistry background really helps you if you're going to go into pharmacology, if you're going to go into medicine, which a lot of people are doing. If you're going to go into nursing, you'll have to take organic chemistry. Now, my background in chemistry in terms of formal education in college is kind of minimal. I didn't really come to love chemistry until I actually started teaching it. And then all the other chemistry that I've picked up over the years is either self-taught or because of special programs that I've been part of during the summer. So, having said all of that, it might be interesting for you to know that many of you have probably had MRIs of a joint or two. I know I've had MRIs on a shoulder and on my knee several times. Magnetic resonance imaging, it's very much like nuclear magnetic resonance, and which is what it used to be called, but early on in this particular field, because patients were nervous or afraid, they had various misperceptions about the word nuclear. The people in hospitals and medicine just dropped the word nuclear altogether. And so it's just called magnetic resonance imaging. Doesn't change the technology, doesn't change the fact that it has to do with the nucleus, but that made people more comfortable with this very, very valuable analytical strategy. So nuclear magnetic resonance imaging involves nuclear spin, and also it's the way it spins and moves about in supermagnetic fields. And of course, in order to generate these very, very strong magnetic fields, you're going to need the materials to make your supermagnets, and it's usually going to be at very, very cold temperatures. I'm guessing right here, because it's hard to read, but I would imagine there's a lot of liquid nitrogen involved here to get very, very cold temperatures. Now, moving right along. So we're going to be doing analytical chemistry. And when you take this course, if you do in college, you're going to be learning about how to operate and take advantage of all kinds of different pieces of information. My research for the Department of Energy out in the Energy Idaho National Engineering Lab for 12 summers used a device in analytical chemistry called the mass spectrometer. And there are many different kinds of mass spectrometers. My mass spectrometer, I call it mine because during the summers I was the only one that ever operated it. We basically, it was designed, invented, it was a prototype, to blast the surface of something with renate ions. And these rather large renate ions would knock any chemicals that might be on the surface of a piece of cloth or metal or plastic or wood or something like that out into a super, super low vacuum. And then these fragments, these particles that were blasted into the vacuum or near vacuum would have a charge to them. And by varying the radio frequency, you could get them to oscillate, and as the oscillations increased, you would capture them in various ways. Mine used a quadrupole, 4 two magnetic tubes, and that was tuned to the particular radio frequency, and so it could count the number of particles according to mass. And as the radio frequency went up, the mass of the particle that it would resonate with or that you would capture would go up, and then you would get a graph, as you can see in the wall in my room. The vertical peaks would be high amounts of these particular masses, of these particular fragments of the original chemicals that were on the surface of something. And then that mass spectrum would be a fingerprint absolutely unique to the particular compound that we were investigating. So it was very, very interesting work, and I learned an awful lot doing that. So, qualitative analysis of a mixture. You'll notice the 2 bullet points here. Did I say qualitative? I meant quantitative, because we're actually going to be able to make, in this section of the chemistry book, in this chapter, we're going to actually be able to measure the amounts of chemicals that are going to be involved. So bullet point number 1, let's say that we dig some ore out of the ground, or let's say we find a sample of a chemical when we evaporate water from a pond or a river or the ocean, or from some sewer water, or some runoff water from a farm, or a battlefield. Let's suppose that however we get this impure substance, we were interested in knowing, especially if it's an ore, what percentage of that mixture of stuff has the particular compound, the particular metal that we are interested in. Obviously, you're not going to start drilling for a particular mineral or a particular metal if it's in very, very low quantities in the Earth's crust. So that's what this is about. We can use stoichiometry and the methods, the rather simple methods in this chapter at this level of chemistry, to determine whether we've got a nice high concentration or a low concentration, whether it's economical to go after it. There's also a form of quantitative analysis that involves combustion as well. So we'll get to these. And so they begin with this example. We have a unknown amount of acetic acid. And let's say, put it into a practical context, let's say that you're working for the Food Drug Administration and you've heard reports that some of those companies that are producing vinegar so that you could buy at Schnucks or Dierberg's or other supermarkets might not actually have the percentage of acetic acid in them that the label says should be in them. And so you're just going to verify that. So how would you do that? Well, one way to determine how much acetic acid is in that aqueous solution, and you'll notice here that this is aqueous. Acetic acid in water is your basic components of vinegar. And so you combine it with a solution of sodium hydroxide. And as a result of that, you get a double displacement reaction. So notice the H on the right, where we could write the formula this way, HC2H3O2. This is how the inorganic chemist would write it. But this hydrogen here is the same as this hydrogen right there. It's the hydrogen that an acid is going to donate. So you have a double displacement reaction. So this is your positive, this is your negative, sodium hydroxide, positive, negative. They swap partners. And then you're going to get sodium acetate right here, sodium acetate. And then you're also going to get hydrogen hydroxide, otherwise known as water, with your positive and your negative charged particles there. And because this reaction produces a liquid, a molecule with a strong bond between the hydrogen and the hydroxide, this goes to the right. Even though you have a weak acid, it will go all the way to the right until every acetic acid molecule has been dissociated, and the reaction stops when you run out when either the acetic acid in the water or the sodium hydroxide is the limiting reactant. Then the reaction stops, and you've gone as far to the right as you can. So we want to find out how much acetic acid is there. What is its percentage? And this is talked about a little bit later in the chapter in section 4.7, and we'll get to that, I think, in a few minutes. That's the kind of thing that we're looking at. Here's another example down here, as far as talking about double displacement reactions and quantitative analysis. You have positive, negative sodium sulfate, positive, negative barium chloride, positive, negative barium sulfate, positive, negative sodium chloride. Does this reaction go to the right? It does, because you have a solid. You either have to be making a liquid, like we said up here, a solid like there, or you have to be making a gas where the reaction reaches equilibrium instead of going all the way to the right. So you can separate the barium sulfate because it precipitates out from the sodium chloride solution. And you'll notice that your sodium sulfate is in a 1-to-1 ratio with barium sulfate according to the balanced equation. So if you take your grams of barium sulfate, that's at the bottom of your beaker, and of course you'd rinse it thoroughly with water. You'd keep pouring off any supernatant liquid. You'd rinse it enough times until you're pretty sure there's no more sodium ions or chloride ions or water. You dry it down, maybe in an oven, or you use an evaporation flask to pull off all the water. You've used those already in the chem lab. Then you can take your grams to moles, and since it's a 1-to-1 ratio, you can convert that into moles of sodium sulfate that must have reacted to produce that many moles of barium sulfate. Then you can convert that into grams of sodium sulfate. And the sodium sulfate is talked about up here. It's in the mineral thenardite, named after a French chemist named Thenard. And you can see that if you get this impure mineral, thenardite, and you use this technique right here, you put your sample in a solution with barium chloride and you react it, and then you get your precipitate of barium sulfate, and you find out how many, and you do the grams to moles, to the right, to moles, and up to grams, you get your grams of sodium sulfate. You can take the mass of your true sodium sulfate and divide it by the mass of the original mineral, and that's how you're going to get your actual analysis of how much sodium sulfate is in that thenardite. Let's see, I'm not going to look at this picture here. I'm going to hopefully come down to here. Let's talk about green chemistry for a bit. Obviously, the thought of being good stewards of God's environment is a very biblical concept and idea. This premise goes all the way back to Genesis chapter 1. It's further developed in Genesis chapter 2, where the ideas of being good stewards, the ideas of serving and protecting, the ideas of having dominion in a biblical sense, those ideas are developed, and in the Hebrew, the Hebrew words for all of those English translations all requires the human being, originally Adam and Eve, to be very, very knowledgeable, as much as they could be, about that part of the environment that they are investigating and studying. Because since God loves his creation, so should we. Since God cares for his creation, as is evident not only in special revelation based on what God says about creation in his own word, but as is evident by looking at creation itself and seeing how much trouble, so to speak, God has gone to provide for the needs of living things, and not just provide the bare necessities, but also to make them interesting and complex and complicated and beautiful. We know that God loves his creation, and so should we. The thing we have to be careful about is our care for the environment should not turn into a worship of the environment. Just because you care for God's creation does not mean you should ever worship it. Romans 1 reminds us you should always worship the creation, not the creator. And so a lot of people with good intentions are very, very concerned about the environment, but it gets to the point where they become very narrowly focused and only look at one particular part of the environment to the detriment of all the others and all the other interactions. And so what they choose to do might have very deleterious side effects or ripple effects that are bad. They might also be more concerned about a particular plant or animal species, for example, than about taking into consideration also, emphasize the word also, what effect does this have on human beings and their flourishing and their prosperity. So a biblical point of view when it comes to green chemistry and anything else in the environmental ideas that stem from Scripture but are sometimes abused is we as Christians would be just as wrong to show no concern for God's creation at all. If I make a spectrum up here, there are within the Christian church, and I think other people as well outside the Christian church, that say we don't need to worry about the environment at all because God made it for us to use any way we feel like it. And some people, even Christians, are saying God's going to torch the whole thing at the end anyway, which is a very sad misperception of what the Bible talks about in eschatology when it talks about the renewed heavens and the renewed earth and the refining fire, not the destroying fire. So that would be that's wrong at one end, but at the other end, it's equally wrong to so worship the environment that you're not stewarding all the other parts of the environment, including the human beings made in God's image. So the Christian perspective is to seek this balance right in between. We want the wise use. We don't want the anything goes kind of use, and we don't want the non-use. Both of those would be wrong. All right, there's another Devo for you. Well, let's do a mineral analysis. Here we have nickel sulfide, and we're reacting it with nitric acid and nickel nitrate, obviously being a nitrate, very soluble. And you'll notice that we have all three reasons for a reaction to go to the right. Now, why would we even do this? So let's suppose that this nickel sulfide comes from this mineral, millerite. Notice that we don't have the formula, which would be a combination of formulas for this mineral. This is a mineral. It forms in the Earth's crust. A lot of minerals will form as a result of volcanic action and then water evaporating and concentrating various minerals. God has filled our Earth's crust all over the place with thousands of different kinds of valuable minerals, some of which we know what to do with and some of which we don't. And he has not distributed them evenly throughout the environment either. Different countries have different concentrations of different minerals. It's almost like God is hoping the nations will kind of get along with each other and trade, which of course is actually what one of his purposes in this unequal distribution of minerals is. We need to form relationships and learn how to get along. So we don't put the formula for millerite here because the other stuff in the mineral isn't what's reacting. The chemical equation is only the stuff that reacts, which is the nickel sulfide in the millerite. And we add nitric acid to it. And in the process, we produce nickel nitrate, which is going to be aqueous. It'll stay in solution. But we're going to precipitate out some sulfur. We're going to bubble away nitrogen dioxide gas. And we're going to create some water, which becomes part of the aqueous solution right there. Now, that water solution, which no longer has sulfur and nitrogen dioxide in it, that aqueous solution of nickel nitrate, now we come down here to the second equation, and we say, all right, we're going to chemically react this with dimethylgloxamine. And dimethylgloxamine is a ligand. It is a solution of a compound in a later chapter in the book. I think it's chapter 22. We don't get to it very much at all because it's the end of the year and it's not in the AP test very much. It talks an awful lot about transition metals and transition metal chemistry, such as nickel. And if you want to remove a metal from solution or from a substance, we often use these compounds like DMG, dimethylgloxine, because they have these little claws in their structure. If you were to look up the structure of dimethylgloxamine, you see it has these claws, and two of these molecules can surround the nickel ion and basically neutralize it. The reason you'd want to do that is because metal ions in things like mayonnaise and salad dressings and so forth, cause those materials to break down, to rot might be a little bit of a strong term, but to make them unedible. And so in order to preserve their shelf life, you want to tie up those metal ions and remove them from any being able to have any activity or reactivity. So we take this nickel nitrate that is in solution, and you add this solution of DMG, and what happens is that the in this mixture, the DMG, dimethylglycine, complexes with the nickel. It takes two molecules to do this. It takes two of these, see the subscript 2, and to surround the nickel ion and removing it. And then it also leaves behind in your solution some nitric acid. And of course, you can then rinse this off and remove the soluble nitrate ions and dry out the water. And now you have this precipitate, notice it's a solid, and you can go from grams when you mass it to moles, and then moles to moles, and then moles to moles. And of course, you'd skip that step because it's the same thing. In this case, it's a 1-to-1 ratio. And then you can go back here, and when you find your moles, and if I'm keeping consistent, moles is down here, and then you can convert that into grams. And that number of grams would be the grams of pure nickel sulfide, and then you would divide that pure nickel sulfide by the original mass of your mineral and get the percentage of nickel sulfide in that mineral and decide if that concentration is high enough that you would be willing to mine it. So it goes kind of like this. When we take those two equations and simplify it into one, we're going to go from our grams to moles. Our stoichiometry part, this was the lower equation, and then this was the upper equation of the two in the previous page, and then we go from moles up to grams. And that's what they do in these steps. And of course, you would do this in one straightforward dimensional analysis problem rather than break it down into details like they're doing here. Here's where they're going from grams to moles, which is this step up here, step number 1. And then they're doing their 1-to-1 ratio right here. There's the 1-to-1 ratio part is right in here. And then in the part 3 is where you go from moles up to grams, right up there. And then you take your grams of pure nickel sulfide, divide it by the mass of the original sample, and you can find that the concentration of nickel sulfide in millerite is 13.8%. And based upon the marketplace, based upon the going rate for the demand for millerite and the need for nickel sulfide in the marketplace, you may or may not decide to mine this at this particular location where you found it. All right, determining the formula of a compound by combustion. This is another way to do a chemical analysis. And in this case, the chemical analysis is especially used when we have organic compounds, particularly hydrocarbons or organic compounds that have carbon, hydrogen, and oxygen. And so we have one example with a hydrocarbon and one example with a compound that contains carbon and hydrogen and oxygen. But in both of those cases, you combust them in oxygen and you produce the usual two byproducts of carbon dioxide and water. And so as we go ahead and look at this in some sample problems, this is what the technique kind of looks like. You would have a furnace right up here, which would surround the container that contains your unknown hydrocarbon. So here's your unknown hydrocarbon. We're calling it CXHY, and our goal, of course, is to find what is X and what is Y. And then, of course, we'd be able to determine its structure at the very end of the entire process. So we have CXHY. We put it into this furnace, and we heat it up until it turns into a vapor, and then we use oxygen gas under pressure to chemically react inside this chamber here with our CH, and then it comes out the right, and it enters the first chamber. Let's call this the first chamber. The second chamber contains a substance that will absorb the carbon dioxide. The substance that they're suggesting is magnesium perchlorate. You'll remember that chlorate is ClO3, and magnesium chlorate is magnesium's a +2, chlorate's a -1. Now magnesium perchlorate is, instead of 3 here, we're going to have a 4. So it's an even stronger oxidizing agent than perchlorate would be. So we're going to combine it with magnesium chlorate to remove the water. Now, usually in a first-year chemistry lab, instead of using a chemical that's kind of expensive and a bit on the dangerous side, per anything that's perchlorate, we would probably use calcium chloride anhydrous. And that anhydrous part should give you a clue why we would use it. Because calcium chloride, when it picks up water, becomes calcium chloride dihydrate. So we use a cheaper way, a more effective way, and certainly with small quantities this would work, we would pass it through calcium chloride. And so now we have our dry CXHY. Now that dry, by this time it's dry, and now it comes into chamber number 3. And in chamber number 3, we're going to remove the other product, which is carbon dioxide. Now, when you remove carbon dioxide, you often combine it with sodium hydroxide. Because you might remember that metallic hydroxides decompose to form metallic oxides and H2O. Let's see, that I don't know if that, but you need to know these equations in reverse. That was the first one that came to mind as an example. But here's a good example. If you remember the movie Apollo 13 that came out in 1995, this was a potentially disastrous Apollo mission. It was in 1970. This was the year that I graduated from high school, so I'm ancient. And I remember hearing about it. And they were getting a buildup of carbon dioxide, which eventually would cause all the astronauts to suffocate, to die. And they had to jerry-rig a way to remove the carbon dioxide. And because of some other things that were in the capsule, if I remember correctly, they used lithium hydroxide, and to absorb the carbon dioxide, and gave them just enough air, literally speaking, uncontaminated air to get back to the planet Earth. Now, in any case, when you pass it through here, the sodium hydroxide combines with the carbon dioxide, and you make a metallic oxide, and which doesn't occupy much space and isn't a gas. So you're removing that gas from the air, and then what comes out here is what's left over is the compound that contains CXHY and sometimes OZ, but not in this case. We'll look at that example a little bit later. So let's see how this plays out when we do an actual problem. Again, our steps are over here on the left. We have an unknown but pure compound. That's pretty important. We're assuming it's pure. We're going to isolate the reaction products are isolated, which means we're removing the water and the CO2. And then we're going to measure the amount of water and the amount of CO2, because that gives us very important information. And we can work backwards from there to see what carbon and what hydrogen atoms are left to make up this compound called CXHY, whatever it is. Here's a schematic diagram showing the process. We burn it in oxygen, we combust it in oxygen. Here's my two products, 1, 2. Once we mass the amount of water and mass the amount of carbon dioxide, which is measuring the mass of the container before and the mass of the container after it has carbon dioxide in it. And when you get the grams of carbon dioxide and grams of water, you convert it into moles, which is done in this step right here. When you have your moles of water and your moles of carbon dioxide, you know that there are 2 moles of hydrogen atoms for every 1 mole of water. Notice here we're now talking about atoms and not Brinkelhoff diatomic hydrogen. Talking about moles of atoms. Make sure every year somebody makes a mistake and thinks that has to be Brinkelhoff. You're not creating any hydrogen gas at all in this reaction. But these are hydrogen atoms that are going to be part of the compound CXHY. And here you have your moles of carbon atoms, because every carbon dioxide has a carbon atom. If I had a dozen carbon dioxide molecules, that would be a dozen carbon atoms. And remember, all of these hydrogens and all of these carbon atoms came from the original sample. That's where they came from. They didn't come from any place else, because the only other thing we added was oxygen gas in order to combust it. Once we know our moles of hydrogen atoms and moles of carbon atoms, we can create this ratio right here. And that ratio can give us the empirical formula. For example, if the formula came out to be 2 to 1, that means my formula would be H2C, or we would say CH2 would be my empirical formula as an example. But we'll find out whether or not they made it nice and simple like that in this example. So hopefully you get the idea of what's going on. And again, I would set up the stoichiometry problem, drawing the big line. Okay, so I would have my grams of CO2, and then I would convert it into moles of CO2 from the grams of CO2. And then from there, once I know my moles of CO2, I want my moles of carbon that are in my moles of CO2, because my grams cancel out, my moles of carbon dioxide cancel out, and that coefficient, let's use a different color, that subscript, 2, gives me the coefficient 2 moles of carbon. You don't want to forget that. And that gives me my atoms of carbon. So here is step 1 right there, and then they do step 2. Here's step 1 for carbon dioxide and water. And then they're going to do step 2 down here. There's your, you know what, I was thinking about oxygen. Let's back up a little bit. Hopefully you caught that mistake. I make these mistakes on purpose to see if you're paying attention. This is a 1, because I'm talking about carbon, not oxygen. I got ahead of myself. There we go. And so this is step 2 right there. And step 2 for hydrogen. There it is. Here's step 2 for hydrogen. And there's the 2 because it's H2O. That subscript becomes the 2. And we get these moles of hydrogen. And by the way, when I said I make these mistakes on purpose, that's not true. I'm doing this in the middle of the summer, and I'm trying to hurry, and I got my phone beside me, and my parents tried to call me, so there are a few distractions here. In any case, now that I have my moles of hydrogen and my moles of carbon, step 3 would be to set up my ratio. And you can see that I have a 2.335 to 1 ratio. Or you could say that you have a 2 1/3 to 1 ratio. Or you could say, because 0.335 is close enough to a third when you get out to that thousandths place. And my 2 1/3 is actually 7/3 over 1. If I take the mixed fraction and turn it into 7/3, and then this equals 7:3 ratio. So my whole number ratio for this substance of CXHY is C3H7. Now when I add up 3 carbons plus 7 hydrogens, I get this mass of 43.1 grams per mole. However, if you went back to reread the original problem said they used a different piece of diagnostic equipment and found out that the molar mass was 86.2. A piece of equipment, for example, like a melting point apparatus. Every substance, every pure substance melts at a particular unique melting point. And so a melting point apparatus, you're actually going to do a lab with a melting point apparatus to measure some aspirin you're going to synthesize later in the class. That apparatus told us that the molar mass was 86.2. So my molar mass divided by we could call it the empirical mass, gives me a 2-to-1 ratio or a 2, which therefore means I just double my formula. And the actual molecular formula is C6H14. Now at this point, there are a number of different ways that we could take 6 carbons and 14 hydrogens and construct a molecule obeying all the rules that carbon has 4 bonds and hydrogen has 1 bond, and that we have 6 carbons and 14 hydrogens. 2 of those isomers are right here and right here. So we'd have to do some more laboratory tests to find out which one of these particular substances we actually have. All right, let's look at example 4.5. This is going to follow the same process with a little bit of additional work to be done, because now our unknown substance also has oxygen in it as well. So my formula is CXHYOZ. We don't know what any of those subscripts are. And if you're looking at the problem, once again, they heat it with oxygen gas. Here's the mass of my original substance. We heat it with the oxygen gas. We find out how much carbon dioxide we produce. When we isolate the carbon dioxide, we find out how much water we produce when we isolate the water. And we convert those values. If we are we measuring them in, let's say the carbon dioxide was collected as a gas and the water was collected as a liquid, we would have to convert it into grams. So once we have grams of carbon dioxide and grams of water, we're going to go through these 4 steps that you see right here. And again, I would do this in one big long line, where you do your dimensional analysis. So step 1, we take our grams, divided by the molar masses from the periodic table or from Google, and we get our moles of carbon atoms and our moles of hydrogen atoms. The next thing that we do, and by the way, let's double check the stoichiometric ratio in the, well, we don't have that, do we? So there's not going to be, we don't know what the formulas are. So at this point, we're not going to be multiplying by subscripts or anything. So we have this many grams of carbon and this many grams of hydrogen. And please keep in mind, this is not Brinkerhoff hydrogen gas. We have grams of carbon, grams of hydrogen. Now, since we know that my original mass was this, and we're going to subtract the carbon and the hydrogen from that, the remaining mass, the difference between the original mass and the sum of these two, is my grams of oxygen atoms. And again, not Brinkerhoff. This is the grams of oxygen atoms. Because remember, these oxygen atoms are embedded in the formula CXHYOZ. There's no oxygen gas in this problem. So now I know my grams of oxygen, and notice I'm going to use 16 here. We're not going to use 32, the molar mass of oxygen gas. Every year there's a student that makes that mistake. And so this gives me my moles of oxygen. So once I have my moles of oxygen and my moles of carbon and my moles of hydrogen, now I can find the ratio of moles of hydrogen and to moles of oxygen to moles of carbon. And then finding that ratio, I can get my empirical formula, CHO2, because it'll turn out to be a 1:1:2 ratio. Where did I get the 1:1 ratio? Well, that comes from finding the simplest whole number ratio of all three of these masses. So if I were to take my 0.137 and my 0.0115 and my, wait a minute, I don't want to do my grams, I want to do my moles, excuse me. Up here with the moles, you can see my 1:1 ratio of carbon to hydrogen. Down here, you can see my 2:1 ratio of oxygen to carbon. And so my formula is going to be CH, which was a 1:1 ratio, 1:1:2, two oxygens. That's the empirical formula. We would need more information to find the molecular formula. Now, very quickly, we want to talk about molarity. Later on, when we have a chapter on solutions, I think it's chapter 13, but you should know from first year chemistry that molarity is defined as moles of solute divided by liters of solution. Notice that this is the overall volume. Obviously, if you were to put some solid solute into a container of water or some other solvent, that's going to change the volume. Now, you would think the volume is always going to go up. And that's not necessarily the case, because sometimes if it's a small amount of solute, the small amounts of solute actually intersperse between the more spread out solvent molecules. And I believe I've come across a couple occasions where the volume actually went down, but you're not going to encounter that. The point I want to make is we only care what the overall volume is, and that way we don't have to get down into the nitty-gritty of trying to determine the volume of adding a solute to a solvent because that would be kind of tedious, and because of the way in which molarity is used all the time, maybe one of the most common ways that the common way of measuring solution is molarity in general chemistry. It's very easy to do. So we just want the overall volume to be measured. And so it's moles per liter. Now, frequently, if we're given the molarity and the volume, we can solve this equation for X moles, and then we can convert the moles into grams. Another way that it's often used is we are given so many grams of a solute, we convert it into moles, and then once we convert it into moles, we can divide by the liters to find the molarity, or if we know what the molarity is that we want, my volume can be my unknown, and I can solve for the volume I'm going to need to create this molarity. And that happens all the time when we set up labs for chemistry classes. So molarity, it's very easy, it's very convenient, and we have a specially designed piece of equipment for molarity, and that's called this volumetric flask. In this volumetric flask, there will be a etching in the glass, and you want to fill that up with solution until the level of the liquid on the bottom of the meniscus is resting on that line. And the word meniscus, by the way, kind of interesting. The etymology of the word meniscus, the Greek word M-E-N-E, meni, or mini, is the Greek word for moon. And from the word for moon, we get meniskos, which means crescent, because the moon is often a crescent. And then when that went into the Latin, instead of KOS, it became CUS, meniscus. So here you have your crescent right there. That's my crescent, thinking of a crescent moon, or maybe it's more like that. But this is a crescent, and we use the word meniscus. So we're not trying to offend any ladies here, just because it has MEN at the beginning. Now, we have many different volumetric flasks. I've seen volumetric flasks as extremely small, maybe a milliliter or part of a milliliter. I've seen some gigantic ones that are 3 or 4 liters in size, and they're very expensive. And we have just about all of these sizes. I don't think we have any 4-liter ones. We have all of these sizes in the lab, and maybe I'll show you a picture of them at some point, and you'll see them in the cabinet in the lab. So basically what we do is we measure out our grams to moles, and the solid comes down here at the bottom. We put the solute down here, and then we add some water and stir it all up. And it's easy to stir up because if you grab it around the neck right here, it's easy to swirl the water around. And as you dissolve the solute, you can keep adding more and more water until the level of the water comes up to the meniscus, where the bottom of the meniscus touches the level of the water in the flask. Now, I will make one caveat, one exception to this rule, and it's called the AA rule. If your solute, if you're mixing a liquid acid especially, and you're diluting a liquid acid, you always start with water, maybe fill it up halfway with water, then you add your acid and mix it up, and then you finish with more water as necessary. But you need to have this starting water in the flask already, because mixing water and acid is very exothermic. It produces a lot of heat, and that heat could cause the solution to actually boil up and splatter out the top of the flask. And if you're not wearing goggles and a face mask and a fume hood, a shield, you could be seriously injured. And I've had a situation like this happen one time in doing some cancer research out at Mizzou one summer. And I misread a label and combined sulfuric and hydrochloric acid. And what I thought was water wasn't, because I was working at a university lab in a lab that university students would use, and it was a mess. And there were all kinds of containers that were poorly labeled and falling off, and containers of who knows what that should have been disposed of correctly years ago. But something happened, and it splattered all over the inside of the fume hood. And I was perfectly safe because I had all the precautions in place, but I had a mess to clean up. Anyway, always be careful. Add acid to the water before you top it off with more water. Now, of course, if you have a solid solute, you don't have to worry about that. All right, so let's say that our lab assistant, and I've had students be my lab assistants and do this for me. I've done this many times. The lab assistant right now, as I make this screencast at my school at Westminster, is Dr. Berry. And let's say that she needed to prepare some potassium permanganate for a lab. Well, she would need to know, according to the instructions in the lab, just how many liters or milliliters of this potassium permanganate solution that she would need. And she would also need to know the molarity. So if you think of the formula, Molarity, capital letter M, is defined as moles of solute per liters of solution. The instructions in the lab would say this lab calls for a certain molarity, and it would also say you're going to need a certain volume for so many students. And you can see then that what Dr. Berry would do is she would multiply the molarity times the volume, which would be in liters, of course, to get the moles of potassium permanganate that she was going to need. And then she would convert the moles into grams and mass out the appropriate mass in grams of potassium permanganate, get out the appropriate size volumetric flask, maybe a 500 ml or a 1 liter or 2 liter or whatever, and then add the solute, the potassium permanganate, into the flask, and then fill it up with water, stirring as she goes. Very nice and precise, very straightforward to do. Now, I will say one thing. We know from experience, teachers, we know from experience that if we had a lab, for example, that required 1 liter of solution for X number of students to do this lab, we generally prepare twice as much. Because there's always some students that misread something, spill something, have to do it over, whatever, because they're learning. And sometimes they're careless. And sometimes they're presumptuous. And so we always make twice as much of what we need. And on occasion, we've even had to make more, but most of the time we do have some that's left over. In the class that I taught last year, there were 4 teams. One team never needed extra solution. They were very meticulous, very careful. They took the trouble to understand why they were doing each step when they did it, rather than follow it like a recipe, a cookbook recipe. I had 2 other teams that were relatively pretty good, and every now and then might need to repeat the lab. And then I had another team that I don't know if they ever did everything right from the first time around all year, maybe once or twice. And that's why I had the extra solution to save time. By the way, potassium permanganate, a beautiful purple color in solution, is a germicide. It's also a fungicide. In the trench warfare, in the world wars a century ago, soldiers often put potassium permanganate into their boots because their boots would get all muddy and soggy, and you could get all kinds of nasty fungi in your boots. And of course, that would make it very difficult, especially if you're infantry and have to be on your feet. Because, as the saying goes, you hate it when there is a fungus among us. Sorry, teacher joke. Okay, so in this particular lab, this particular example that's embedded in the text, if we take our 435 grams of potassium permanganate, we convert it to moles, and of course you'd be doing this using dimensional analysis, canceling out spectators as you go, and being extra careful with the stoichiometric coefficients. We get our moles of potassium permanganate. Once we have our moles of potassium permanganate, if you remember the formula, moles per liter gives me molarity. Now, by the way, see these brackets? The brackets mean molarity. Same thing. And when you get your answer, by the way, this is another mistake that students make, you can't just say this. You have to write the capital letter M for molarity with your answer. So any way we take our moles and divide it by our volume, we're probably using a 250 milliliter volumetric flask here and stirring it up, and we get the molarity of the solution is right there. Now, keep in mind, and this is an important point coming up that students often forget, that assuming we have a relatively dilute solution, you have more than enough water molecules to completely dissociate all of the potassium permanganate crystal. You notice this is going to be very soluble because it's a potassium compound. And so every potassium and permanganate ion in the crystal is going to be surrounded by water molecules and separated from each other. And so if I have 1 mole of potassium permanganate salt and I put it in water, I'm going to get 1 mole of potassium ions and 1 mole of permanganate ions. Don't make the mistake and say, oh, if I have 1 mole of potassium permanganate, I'm going to get a half a mole of potassium ions and a half a mole of permanganate ions. Not true. Think about a Mormon square dance, if I can be a little humorous, maybe not in a polite way. Let's say you have 1 guy and 2 girls. For whatever reason, at a dance. If they were all to split up, you don't get 1 guy and 2 girls, but you get 1 guy and 1 girl and another girl. The point being is that completely splitting up, you want to make sure that you keep the 1 to 1 to 1 ratio. Of course, if we had copper 2 chloride, remember this is copper Roman numeral 2, that's why you have 2 chlorides. If I had 1 molar of this, and that would be pretty concentrated, so you'd probably have 1/10 of a molar. This is more realistic. You would not necessarily know this, but I would. So 0.1 molar. You're going to get 0.1 molar of copper 2 ions, and you're going to get 0.2 molar of chloride ions. Notice that 0.1 molar turns into 0.1 molar plus 0.2 molar. Make sure you remember that. And when you're adding your water, like this picture suggests, once you get to the neck part, you would use your wash bottle. I would prefer that we call this a DI water bottle, deionized water or distilled water bottle. Sometimes a wash bottle just might have water in it, regular tap water. But when you get to the neck part, since you want to measure very precisely up to the meniscus, you would use your DI bottle, plastic bottle, to get those drops in there just to the right place. You can also use a pipette, for example. So here's a problem. If we have 25.3 grams of sodium carbonate, we dissolve in enough water to make 1/4 of a liter of solution. What's the concentration? And we always begin by remembering that this is not a chemical reaction because we're dissolving. Dissolving means the ions are dissociating from each other. Dissociation is the opposite of the word associate. Associate, come together. Dissociate, to do just the reverse. So there's my equation. I need to keep that in my mind. But step number 1 is I convert my grams to mole. And when it comes to finding the concentration of solutions, frequently I begin my stoichiometry with my solute in the numerator and my solvent or the solution, depending upon what problem I'm working on. And the molarities, I would have solution in the denominator. And then I would, in my dimensional analysis, I would convert my grams of solute into moles. That's step number 1, which is done right here. And then, if necessary, I would convert my volume into liters. If it's in milliliters or some other unit of volume, I would convert my volume into liters. And of course, this is already in liters, so we don't have to do step number 2. Step number 2 is not necessary. And you can see that my units, the only units left are moles per liter. The others have canceled out, so that is molarity. And then my molarity of my sodium ions, notice the 2 right there. So in my molarity of sodium ions, I have to multiply it by 2 because I have twice as many sodium ions as I have carbonate ions. Now, the last example of preparing solutions for a lab is when your solute is in solution and you want to dilute it. When you want to dilute your solution, we use the technique that I'm about to talk about here. I should mention something though, first of all, and that is that oftentimes when we buy chemicals from the chemical supply companies that we do business with, they will market concentrated acids, for example, or other solutions at high concentration. And you buy the solution at a high concentration, and then as you need it, you pour off a little bit of the high concentration and dilute it with water to get the low concentrations you might need in your research or in your lab activities. So in a chemistry lab, we will be doing the procedure that you're about to see, and hopefully you remember it from last year. We do this all the time. Now, the idea of dilution can be illustrated like this. Let's say I have 10 young ladies in my classroom. And there's 10 guys in the classroom. Now, if 5 more guys walk into the classroom, I haven't changed the number of ladies in the classroom. It's just that the concentration of ladies in the classroom has gone down. So the point we're trying to make is if I have a certain amount of solute in solution and I add water, the amount of solute in the solution hasn't changed, but its concentration has gone down. It's become more dilute. You need to make sure you understand that concept. So when we do problems like this, and in this particular example, the goal is to make 2 liters of 1.5 molar sodium carbonate. We want to make 2 liters of 1.5 moles of sodium carbonate. For example, the lab technician, or you, this is a nice way to help put your way through college, working for the chemistry department and being a technician, working in the lab and setting up labs for the professors. If you're dependable and trustworthy and a good worker, this can also reduce your tuition costs as well. Something to think about. So let's suppose the professor has determined that he or she needs 2 liters of 1.5 molar sodium carbonate solution. And so your job is to prepare it. Now, before I continue on with the math, let's remember something. Liters times molarity equals liters times moles per liter. The liters cancel, equals moles. So whenever we multiply volume times molarity, we're always going to get moles. Notice that the moles doesn't change no matter how much water you might add later on. Just like the number of girls in the classroom doesn't change no matter how many boys walk into the room. And another hint, whenever you're given the volume and the molarity of something, chances are you're going to have to multiply the two together at some point. That's very, very common. When we get to acid-base chemistry and buffers and titrations, that happens an awful lot. When in doubt, multiply the volume of a solution times the molarity of that solution to get moles. It probably is going to come in handy. So in this particular case, here's your 2 liters of solution. This is your volume. And then here's your molarity. Molarity is 1.50. Notice moles per liter is molarity. Same thing. Per, of course, P-E-R, means put it in the denominator. If we're talking about finding the percent, you're going to put 100 in the denominator. And if it's 27%, 27 goes in the numerator. So notice that my liters cancel out. Moles is the only unit that is left. And I'm going to need 3 moles of sodium carbonate. Once I know how many moles of sodium carbonate I need, then I'm just going to do my dimensional analysis and convert it into grams. Go to Google or whatever and find your molar mass of sodium carbonate. I would prefer you always go to the hundredths place for molar masses. And I'm going to need 318 grams of sodium carbonate. And therefore, I'm going to put that into my 2-liter flask and add some water and stir, add some water and stir, add some water and stir. When I get up to the neck of the volumetric flask, I'll use a pipette or an eyedropper or my squirt bottle to get just the right amount of water. And it's precise enough for much of the chemistry that we typically do, aqueous chemistry that we typically do in first-year chemistry. Now, if my solute is let me back up. If I need to dilute a solution, I'm going to use the same equation. VM equals VM. VM stands for moles, so moles equals moles. I'm not changing the number of girls in the classroom. I'm not changing the amount of salt or potassium permanganate in solution, but by adding water, I'm diluting it. And you can see that in a concentrated solution, you have a high molarity and a low volume of overall solution. But when you add a lot of water, you increase the volume of solution, which forces the molarity to go down. And it keeps the number of moles constant. So if I have a solution of potassium permanganate, maybe I said I do not want to go to the trouble and try to make in my chemistry lab 0.100 molar potassium dichromate. Boy, getting that third significant digit there would be kind of tricky. I'm in a hurry. So I could order it from the chemical supply company, and they could ship me, let's say, a whole liter or something like this of 0.100 molar potassium dichromate solution, very precisely and professionally made. And then I'm going to dilute it. Depending upon what my lab needs, I am going to dilute it. So I'm going to take my concentrated potassium permanganate solution and let's see, I'm going to take my concentrated solution and I'm going to know its molarity because it came from the chemical supply company, but I don't know how much of it, what volume of that concentrated liquid I'm going to need. But I go look at the instructions in the lab, or I go look at the research that I'm doing, and I say, I think I need such and such a volume of such and such a concentration of this solution. So I know 3 of my 4 variables, and I'm going to solve this equation for the volume of my concentrate. And when I solve it for my volume of my concentrate, which actually occurs right here, here's your molarity times volume to get your moles. And then once you take your moles, here is the liters per mole, and you get your volume. And this is 5 milliliters. So I will get out a pipette, most likely, and a pipette that's maybe 10 mils, or if I have one that's exactly 5 mils, and I will pull solution up out of my concentrate into the pipette until I have 5 mils. Decades ago, they used to use their mouth to suck, so to speak, the liquid up. And of course, if you overshot it, you'd get the chemical in your mouth. Not a good idea. Nowadays, we have various devices that you're going to use in the lab, including electrical devices that will pull the liquid up for you into your pipette. And then once it's in my pipette, I stick my finger over the top of it so it can't go out, and I take the whole pipette and I move it over to my larger volumetric flask that has the volume that I want, in this case 500 mils, and let all the liquid out into there of the concentrate, and then I add water and top it off with the squirt bottle to get just the right volume. And that's a good skill to know how to do. And so here's a review of preparing a solution by dilution. This may be the first time you've seen the letter C being used for concentration. I always like to use the word M because we're typically talking about molarity for my concentration. So instead of CV or VC, I like to use VM or MV and when I use this equation. And most commonly, I use volume times molarity equals volume times molarity. You're going to see this equation used in other ways as well, like when we get to electrochemistry and we do titrations, or and we want to have reducing agent and oxidizing agents equaling each other, or especially when we get to acids and bases, and where we want our concentrations of our moles of acid to equal our moles of base. We do this a lot. But right now I use the little letter C for concentration and the little letter D here for dilution. So I have my VM for the concentrate and my VM for the dilute. And again, the number of moles doesn't change. But as the volume of solution goes up, the molarity goes down. Remember, molarity is not the same thing as the number of moles. Make sure you know that. And so here's a pretty simple problem where they give you the volume of your concentrate that they want, and they give you the molarity of your concentrate, and they give you the volume of the dilute that they want, and you have to solve for the molarity of the dilute, of the solution that you've now created. And the last thing in this section is called serial dilutions. Now, serial dilution does not mean adding milk to your cornflakes, because that would be this word right here. Teacher joke, chemistry joke, okay? We're not talking about that kind of serial dilution. Serial means something that is repetitive. If you think of in forensic science and criminology, we're often trying to find out the serial arsonist, because a person who is an arson often becomes fascinated by that and commits more arson. And you can have other types of serial criminals as well, which is extraordinarily tragic. And this serial dilution is often called the Mohr method, and the Mohr method is named after a German chemist named Carl Friedrich Mohr from the first half or so of the 19th century. He died in 1879. And one of the things he invented was the Mohr pipette. So you would be using your Mohr pipette right here. You'd be using your Mohr pipette to take a certain volume out of here and put it in there. And then, so as not to change your molarities, you would take a second Mohr pipette, throwing away the first one. Or if you're cheap like me in the lab and are working with high school students, you just rinse it out, and it shouldn't make too much of a difference. And then you would take a sample from there and then put it into there. And you can do a serial dilution 2, 3, 4, 5 times. And the reason is it's better to take a small sample from a large container rather than to try to take a very, very small sample and skip the serial dilution part. But all the way through here, we're using VM equals VM, VM equals VM. And if you do it systematically, you might be diluting it by a factor of 10, for example, or by a factor of 2 each time. And then it's very easy to calculate what your diminishing molarity is as you go along. And we'll stop here.